In this video, we will talk about the method of lines in Mathematica. In particular, we're going to talk about how to solve time-dependent differential equations. So let's consider a function u, a scalar field u. That's a function of time t and position x. And let's suppose that we were in one dimension for now. The partial differential equations that we will consider are of the form partial t of u, that's a partial derivative of u with respect to t, equals L of u, where L is a differential operator. It may or may not be a linear operator. Some examples of this kind of equation can include the Advection Equation, which is of this form. So partial x is partial derivative with respect to x, and c is the speed of the waves. Another equation of this form is the Diffusion Equation. This is of this form. Now we have a constant kappa and a second derivative with respect to x. These are both linear equations. So in this case, the operator L is a linear operator, and it's simply c times partial x here. In this case, it's k times partial x squared. So it's a linear differential operator in both of these examples. So these are linear partial differential equations. Another example of a linear PDE is the Shrediger Equation, and this is of this form. Where h is the Hamiltonian. So right now this quantity L is minus I, h is the L is the linear operator, and the Hamiltonian is minus 1 over 2m, where m is the mass of the particle, partial x squared plus v. So this is a linear equation. H is also a linear operator, so L is a linear operator. Another example is the Burger's equation. This is an example of a nonlinear equation. So this is of this form: partial t u equals minus 1/2 partial x of u squared. So because we have u squared here, in other words, this is minus 1/2 u partial x u. This is the implicit Burger's equation for zero viscosity. We have a nonlinearity here. We have a term u squared, or in other words, u partial x u. So now the L operator depends on u. So in this case, L is minus 1/2 u partial x. Okay, so with that in mind, let's introduce the method of lines. So the method of lines amounts to discretizing our PDE first in space and then in time. So let's introduce a grid. So a set of grid points xi, and let's evaluate our function on those grid points. So we will have ui of t. We will use that to denote u of t and x evaluated at x equals xi. So this means that u is now a vector. It depends on time, but it is a vector, and each component is labeled by the index I. So this is now represented by the vector u, which is a function of t. And that means we can rewrite this equation, partial t u equals L u. This will now have the form du by dt equals L of u, where L is some operator. It may or may not be linear. If the equation is linear, like in some of the examples we saw earlier, for a linear partial differential equation, L is simply a matrix. So this will become du by dt equals a matrix L dotted onto the vector u. In the nonlinear case, L will also be a matrix, but L itself may depend on u, like in the Burger's equation that we solved before. So, in other words, if I write this in terms of the components ui, that would be du I by dt is going to be equal to sum over j, sum over all grid points over ij uj. So clearly this sum over j, lij, uj, we have a summation over j, and summation over adjacent indices means a dot product. So this is the dot product of the matrix L onto the vector u. So if we look at the equations we introduced earlier, so for example, let's consider the Advection equation. Let's rewrite it again. So it's this equation here. Upon discretization in space, this will become an equation of this form, du by dt equals c, and then partial x will become a derivative matrix that we have seen earlier, dotted onto the vector u. Okay, so this is the Advection equation. Now, if you don't know what the differentiation matrix is, please go back to the video where we discussed finite differencing and pseudospectral differentiation or numerical differentiation in Mathematica. Now we have discretized our equation in space, and what that has accomplished is that we have converted a partial differential equation to a system of ordinary differential equations. So the system of ordinary differential equations are coupled through the operator L. So we have one differential equation for each component of U. So U1, U2, U3, and so on, up to UN for all grid points. And these are all coupled. All these ordinary differential equations are time dependent, and they're coupled through this matrix L. That means we can apply all the methods we learned earlier for ordinary differential equations. We can apply them to partial differential equations and treat them as systems of systems of ordinary differential equations. So we can apply Runge-Kutta or the trapezoidal rule or Taylor methods or the Hermite rule and so on. So we will do an implementation, an example of this in Mathematica in the next video. In this video we will write down the schemes in matrix form before we implement them. So if we have an equation of this form, let's call it there's a problem with the tablet. Let's see. So we have an equation of this form, du by dt. Let's call it equation 1. We can integrate it in time, marching forward. So u at time n plus 1 minus u at time n is the integral from tn to tn plus 1 of L of u of t dt. And then all we have to do is approximate this integral. Now, one way to approximate this integral is to do the trapezoidal rule, or we can do the Hermite rule, or we can do a Taylor expansion, and so on. Instead, let's first consider a Runge-Kutta method. So, first of all, let's denote by delta t. It's the time interval or the time step tn plus 1 minus tn. Let's consider a second order Runge-Kutta method. The method I'll be using is from a paper by Gottlieb and Shu. If you simply Google TVD Runge-Kutta, it's the first paper that will show up. So let's consider a second order Runge-Kutta method. That's TVD. That stands for total variation diminishing. That's not important right now. We could use a standard Runge-Kutta method if we wanted. But the notation in this paper is convenient because it matches our notation. So that involves two steps. So to go from un to un plus 1, we have one intermediate step. So we start with un as a given, and then we compute an intermediate vector u1 that is equal to un plus delta t times L of un. And then the next step, un plus 1, is given by 1/2 un plus 1/2 u1 plus 1/2 delta t L, that's the operator L, u1. Now, if L is a linear differential operator, if our equation is a linear PD, then we can combine those two steps into one. If we simply take u1 and plug it in here, and also plug it in here, if we substitute, then we get, in the linear case, we get un plus 1 equals un plus delta t L dotted onto un plus 1/2 delta t squared L squared. So that's the matrix L squared dotted onto un. And if we look at this, we can factor out the vector un. We'll do that in a minute, but before we do that, if you look at this integral, if L is a linear differential operator, then we can Taylor expand u of t about tn, and then integrate that Taylor expansion from tn to tn plus 1. And if we integrate that Taylor expansion, we will get precisely this formula. So essentially, for linear PDs, if L is a linear operator, then a Runge-Kutta method gives the same result as a Taylor expansion. So with that in mind, let's factor out the vector un. So that will leave us with a unit matrix here plus delta t times L plus 1/2 delta t squared L squared. So this is some matrix L dotted onto the vector un. And I don't need these brackets here, but I'm having some difficulty erasing them. Okay. Okay, so now each time step, to go from one time step to the next, again, I don't need these here. So to go from one time step to the next, from un to un plus 1, all we have to do is one matrix multiplication. And in particular, if the equation is linear, we can actually construct this matrix in advance and store it. So L, in the case of the Advection equation, for example, L will be this matrix C times D, where D is the differentiation matrix, which we know how to compute for finite differences or for pseudospectral methods, Chebyshev collocation methods, and so on. If we simply construct this matrix C, C times D, and store it, then we can multiply by delta T, add it to the unit matrix, and add this extra term, and then store this whole matrix. And we can call this matrix, let's call it M. and then each time step is simply a matrix multiplication, m dot u. So we can simply do a do loop for n going from 1 up to some number, whatever the number of time steps is. So if we want to do 100 time steps, that would be 100. And this is the quickest PD solver of all time. It's a very simple do loop. And again, the spatial differentiation, it can be finite difference or pseudospectral. All you have to do is change one parameter when you construct the derivative matrix. We will see examples of this in the next video. So that was a second order Runge-Kutta method. Let's consider a third order Runge-Kutta method from the same paper. The paper is by Gottlieb and Shu. So let's consider RK3 TVD, total variation diminishing. So in this case involves two intermediate steps. So U1 is UN plus delta T L of UN, and this is true whether the equation is linear or not, the way it's written here. And then the second step is U2, and that's of this form. And then finally, UN plus 1 is given by this expression. So what we have to do here is compute U1 from UN, and then U2 using UN and U1, and then UN plus 1 is computed from UN and U2. So we calculate those two intermediate steps, and then the next step, UN plus 1, is given by this expression. Again, these expressions are true for generically whether L is a linear or nonlinear operator. If L is a linear operator, then all these steps can be combined into one and simplified. So for the linear case, if we combine all of these steps, so take U1, plug it in here and in here, and then take U2 and plug it in here and in here. So if we do these substitutions and sum up all the terms, then what we get is, for the linear case, we get unit matrix plus delta T times L plus 1/2 delta t L squared plus 1/3 factorial delta t L cubed acting on UN. So what we see is that this amounts to adding an extra term of the Taylor expansion to this matrix here. So we could have obtained the same result by Taylor expanding U as a function of t about t equals Tn. So, and then integrate that Taylor expansion. And for a linear equation, L is a constant matrix. It can be pulled out of the integral. So integrating the Taylor expansion U of t is simply a matter of integrating a polynomial. And the order polynomial is one order higher in this case compared to this case. So here actually we only have to expand U to first order. And here we have to expand U to second order. And after we integrate, we will get this expression. So another way to see this is to consider the fact that the discrete version of the advection equation, for example, or any equation of this form, du by dt equals L times U. If L is a linear operator, then this equation upon discretization in space will have a matrix L, which is it does not depend on U. So it's essentially a constant matrix. If we consider this linear equation, then the solution of this type of equation is known. So we know that the solution is U of t is e to the L t times the initial vector at time 0. And so now we can see that if we do a Taylor expansion of, so if we consider, for example, U at time n+1, that's e to the L times delta t times U n. Now this is an exact result. And if we do a Taylor expansion of this exponential, e to the L delta t, we know that this exponential has a Taylor expansion that's precisely of this form, the quantity that is in brackets here. So that's another way to see that a Taylor expansion of this operator matches what we obtained here with the Runge-Kutta method. Okay, now as we discussed before, the Runge-Kutta methods are not time symmetric. So even though this operator e to the L delta t, if we do a time reversal, it's symmetric under time reversals. So if delta t changes to minus delta t, then un+1 and un change place, then this equation stays the same. However, this is not true for the discrete version. So this equation here, where we have approximated e to the L delta t by a Taylor expansion, this breaks this symmetry. And in practice, this means that certain symmetries of the exact system will be violated upon time discretization with such methods. For these symmetries to be respected, we can consider time symmetric methods. You can go back to the previous video, which talks about implicit methods and the Hermite Rule in Mathematica. And we can consider this class of methods here as well. So let's consider this integral again. This integral of L times U. And let's consider using the trapezoidal rule or the Hermite rule to calculate that integral. So let's write it down again. So implicit methods. So U at time n+1. By the way, UN stands for U at time Tn, and so on. So UN+1 minus UN is the integral of L of U of T dt from Tn to Tn+1. And for simplicity, let's consider the case where L is a linear operator for now. Then L can be pulled out of the integral because it's a constant matrix that's independent of time. And then if we use the trapezoidal rule, this will be L times delta t, so that's the height of the trapezoid, times the small base plus the big base of the trapezoid divided by 2. Okay, so now this is our scheme. So this is the trapezium or the trapezoidal rule. What we see here is that this is an implicit scheme because UN+1, the next step, appears in both sides of the equation. Now, in general, if this was a nonlinear equation, the way you would solve this is at each time step you would make an initial guess for UN+1, or you could calculate it with Euler or a Runge-Kutta method. You would calculate an initial guess for UN+1, then you would plug this here, evaluate this term, and use it to calculate UN+1 from here. And then you would take this value of UN+1, you would plug it back in here, evaluate this whole term, calculate it again, take the result, use it to evaluate the new UN+1, and then go back and substitute again and again. So you would do that a few times, maybe 5 times, maybe 10 times at each time step until the result no longer changes, and then you would know this is your UN+1. And then you would move on to the next time step. Now, this is called the self-consistent field method or fixed point method. It's a fixed point iteration. In this case, however, if we assume that L is a linear operator, then we can actually directly solve this equation as a linear system. So let's do that here. It involves very little algebra. So we want to pull UN+1 on one side of the equation. So if we collect the terms u n plus 1, and then we will have minus L delta t times 1/2, and then u n plus 1. And then on the other side, we can take this un to the right hand side. We'll have un, and then this term right here, plus 1/2 L delta t un. And now we can actually factor out the u on both sides. So the left hand side will become unit matrix minus 1/2 L delta t dotted onto u n plus 1. That's a dot product matrix dotted onto a vector. And then on the right hand side we will have unit matrix plus 1/2 L delta t dotted onto un. Now this is a matrix multiplying un, and we can simply invert this matrix using the inverse command of Mathematica. So we can use inverse to invert this matrix. That means the equation will be written like that. U n plus 1 is unit matrix minus 1/2 L delta t. So we can multiply both sides by the inverse of this matrix basically, and then that will be dotted onto I unit matrix plus 1/2 L delta t, and then that will be dotted onto un. So we can call this matrix M, and we can store it, because again, if delta t time step is fixed and the matrix L is fixed, then this matrix doesn't change in each time step. We can simply store it in advance, and then each time step again is a simple matrix multiplication. So in this case, the performance of this method, because it just involves a matrix multiplication at this time, each time step, the performance will be the same as the Runge-Kutta method, where again we have one matrix multiplication at each time step with a matrix that is pre-calculated and stored in memory. So for implicit methods, if the equation is linear, then we can convert the method to an explicit method essentially, but it preserves the properties of the implicit method. In particular, we will see when we implement this that because this discretization is symmetric under time reversal, because it's time symmetric, if you change delta t to minus delta t, this equation stays the same. So this equality, if you change delta t to minus delta t, then un plus 1 and un change place, the minus sign cancels, and we get the same equation essentially. And you can see that here as well. If delta t changes to minus delta t and un plus 1 and un change place, we're left with the same equation. So this discretization respects time symmetry, time reflection, and so for linear PDEs, we'll see that it conserves energy. From nonlinear PDEs, it may not conserve energy exactly, but it will conserve it on average. Now calculating this inverse here, if you just do it once and store it, then the cost is a one-time issue. You don't have to do that inversion at each time step. However, you do have to do a matrix multiplication at each time step, and that scales as n squared the cost of that operation is n squared, where n is the size of the matrix. If we use pseudospectral methods, then the matrix L is a full matrix, so M will be a full matrix. In any case, and both of these matrices here and here will be full, so all M elements will be non-zero. So there's no better way to do this. The best way to do this is to do this matrix multiplication. However, if we use finite difference methods, then the matrix L is sparse, which means that unit matrix plus this term will be a sparse matrix, and the same is true for this matrix on the left-hand side. But if we invert this matrix on the left-hand side, the inverse, which is going to be this term, is not going to be sparse anymore. It's going to be full matrix. And so this matrix M is not going to be sparse anymore. So in that case, we have an n squared cost because M is a full matrix. However, if you use finite difference methods, then it may be better to use something called the Thomas algorithm, which means you can invert this matrix at each time step, and that the cost of that is actually linear in n, the size of the matrix. So if you use the Thomas algorithm, that inversion can become faster for finite difference methods, and that's automatically implemented by Mathematica if you use the command linear solve at each time step to solve this system of equations for the unknowns un plus 1 in terms of all of the other terms that are known. Then that will be done faster compared to this matrix multiplication. And again, this is advised if you use finite difference methods, so that L is a sparse matrix, then that's the fastest way to do it. If you use finite difference, if you use pseudospectral methods, then the Thomas algorithm does not apply anymore because these matrices are not sparse. So in that case, it's better to just invert this matrix, store it, and then use matrix multiplication at each time step. Finally, I want to talk about the next order correction to this method. So the trapezoidal rule is a second order method. If we want to calculate this to higher order, we can use the Hermite Rule or the Lotkin rule, which are fourth order and sixth order respectively. So let's consider the Hermite Rule. So we would have this equality again. We would have to calculate this integral right here. And L is a constant matrix for the linear case. And if we apply the Hermite rule to this integral, then we pick up that trapezoidal rule plus some extra corrections. So let's write down the result here. So that involves approximating this integral u of t dt, and that's equal approximately to un plus un plus 1 divided by 2. That's the trapezoidal rule. And then the correction is delta t squared un dot minus un plus 1 dot divided by 12. So that's the familiar Hermite rule that we have seen in the numerical integration video, and that's fourth order in delta t. Now, if we use this approximation here, we're going to have the matrix L multiplying this expression, and then that will be equal to this. So let's write this down. So U and okay. Plus 1 UN plus 1/2 delta T L. So that's the first term from the trapezoidal rule, which is UN plus UN plus 1. And then the other term is 1/12 delta T squared. And then we have UN dot minus UN plus 1 dot. Now, if we look at these time derivatives, UN dot and UN plus 1 dot, in this case, we know these derivatives exactly from the differential equation itself. Remember, the differential equation is this for the linear case. So du by dt, or u dot, is simply L times u. So we can replace the dot, the d, or the d by dt operator with the L operator, simply because this is the differential equation we're solving. And if this was a nonlinear equation, then we could again replace du by dt by L of u, and so on. So let's do that here. So this term right here will become 1/12 I forgot to put an L here. There was an L there. And then we'll have delta T squared. And now, again, we replace u dot by L times u. So, and again, u dot here, L times u. So that we'll pick up an extra L operator, which we can pull outside the parentheses. So this term L will become L squared. And then we'll have u n here, and then u n plus 1 here. Okay, so this is nice because now we can collect all the u terms and the un plus 1 terms as we did before with the trapezoidal rule. And it's also nice because the time derivatives are known exactly, and we take advantage of that fact that we know the time derivatives exactly from the differential equation. Now, if we were to do Lotkin's rule, we will have u double dot, some correction terms with u double dot. And those terms, again, could be obtained by taking a time derivative of the differential equation. So if we take a time derivative of this equation, we will have u double dot equals L times u dot. And then u dot will be replaced by L times u. So that means u double dot will be L squared times u. So we can keep doing this for any order of the equation. In fact, this is how we get this Taylor expansion, by replacing u dot, u double dot, and so on by L L squared times U, and so on. This is another way to produce these Taylor expansions here. Okay, so now let's collect all these terms. So on the left-hand side, we have unit matrix, which is what multiplies UN. And then we'll have this term here with a minus. Once we pull it to the left, it will be minus delta T over 2 times L. And then we're going to have this term right here. It's a minus, so it will become a plus when we take it to the left side. So it'll be delta T divided by 12 times L squared. And then all that will multiply the vector UN plus 1. And then on the right hand side, we will have this term UN. So that's going to be unit matrix. And then this term. So plus 1 delta T over 2 times L. And then finally this term right here. So plus delta T squared over 12 L squared, and that will be dotted onto UN. Now again, as before, we can either use the Thomas algorithm to invert this matrix or solve this linear system. We can use linear solve if L is computed using finite differences, or we can simply invert this matrix and store it. If we use pseudo-spectral methods, that would be more efficient. So in the end, we can multiply both sides with the inverse of this matrix, and then the final result would look like this. So unit matrix minus delta T over 2 so that will be the inverse of that matrix dotted onto this matrix right here. So delta T over 2 times L dotted onto UN. Okay, so now this is essentially our matrix M. So again, each time step is simply a matrix multiplication. So it becomes extremely easy to evolve a system like that. So M dotted onto UN. So all you have to do is compute the derivative matrices, then use those to compute L, use those to compute this matrix M. This inverse can be computed with an inverse command in Mathematica, and then inside a do loop, we'll simply do a matrix multiplication. Now we begin to notice a pattern here. If you look at, before we had the trapezoidal rule, we had this term and this term. Now we pick up some corrections. And as we mentioned before, the solution to this equation is of this exponential form. So the Taylor method amounted to expanding this exponential e to the L delta t, doing a Taylor expansion for small values of delta t. So we expand about delta t equals 0. These methods are time symmetric. So what we can do, as we did for when we discussed the ODE of this form, which was du by dt equals lambda times u. That was a one-dimensional ODE for a scalar function u of t. Now we have a system of equations that are coupled through these matrices, and as we said before, the solution to this equation was u of t equals e to the lambda t times u0. The solution to this equation that we wrote above is u of t equals e to the l t times u0, where e to the lt is the matrix exponential. And as we discussed then, one can calculate the Padé approximant of this exponential. So you can use the command Padé approximant in Mathematica to confirm that e to the L delta t is unit matrix plus delta t over 2, and then unit matrix minus delta t over 2. So if we ask Mathematica to calculate the 1-1 Padé approximant, it will give us this expression, and that will match what we got here for the trapezoidal rule. And this inverse is expressed by having this matrix here in the denominator. What we mean by that is inverse matrix times this matrix, and this appears on the left and this appears on the right. If we ask Mathematica to calculate the 2-2 approximant, then it will calculate this to order delta t squared, and the numerator or the matrix on the right will be will pick up these corrections. I forgot the L here, and then there will be an L squared. So we see that what the result that we get using the Hermite rule is equivalent to what we could get using a Padé method, expanding the exponential using Padé approximant. However, I have to say that the Hermite method is more flexible because if you try and solve a nonlinear equation, then you can no longer apply this. The exponential is only a solution for linear PDEs. It's not a solution for nonlinear PDEs. Whereas the Hermite method can be applied for linear or nonlinear PDEs. And also, if we have systems that involve more variables, as we will see when we discuss the wave equation, again, it will prove that it will prove to be more convenient to use the Hermite rule. And finally, let's briefly discuss the Schrediger equation. So let's consider the Schrediger equation, and let's consider let's suppose that the h bar, the reduced Planck constant, is 1, that the mass is 2 of the particle, and that the potential is 0, so that's a free particle. Then, just for the sake of simplicity, then the Schrediger equation is of this form. Or in other words, it's of this form where h is a linear differential operator involving a second derivative. If we discretize this problem, then this Hamiltonian will amount to a matrix. If we discretize in space, that would be I times d squared, where d is the differentiation matrix for our grid. And again, we can discretize this using finite differences or pseudospectral methods. Now, for pseudospectral methods, we could use, for example, Chebyshev collocation methods, or we could use a Fourier method. That would mean we're using trigonometric interpolation, and we use that to calculate the derivatives and to calculate the differentiation matrix. The benefit of doing that is that in this case, D would be symmetric, so it would be a Hermitian matrix. Whereas for the Chebyshev case, it's actually anti-symmetric, and that's not good. The reason it's not good is that if we look at this expansion, now the solution in this case looks exactly like that. Just replace L by H, essentially, and it looks exactly like that. So the solution is C of t equals e to the ht, and then we can consider the Padé approximant e to the h delta t, and that would look exactly the same as before if we replace L by H. Okay, so now we see that H being symmetric is very important, because it means that this matrix will be Hermitian. That means the magnitude of e to the h delta t will be 1. And the modulus of that quantity. Remember, h has an I here. So e to the I times some real numbers, the modulus will be 1. If h is not symmetric, then the modulus of this expression will no longer be 1, so we would lose unitarity. That means if h is symmetric, then this discretization will conserve probability. So this result is exact. If h is symmetric, like with Fourier discretization, then this result will also hold after we discretize. But if we use Chebyshev methods here, then this will no longer have a unit modulus. If we use finite differences, then these differential matrices are also symmetric for finite differences. So in this case, this is also symmetric. So that's also okay. That preserves unitarity. Okay, so with that, I will conclude this video. In the next video, we will implement this method in practice and see how we can solve an advection equation or wave equations and so on.